Hi, everybody. So I'm going to try and explain the rest of the things about this neck joint that I use. First, I'll just say that I've been very happy with this. I put it in my first guitar, the Frankentop guitar, which you all can see in Riff 19. If you haven't checked it out, it's a worthwhile show to see. I have never had a failure with it. It's really been a fantastic system. And the basic way it works is that there's a sleeve made of aluminum that's glued into the neck block. You can see there it is positioned in the neck block, and there it is installed in the guitar. So the way this is designed to work is that the action is adjustable in this direction, and this pin is not quite square to the fingerboard surface, but rather tilted a little bit kind of the wrong way. It goes this way. And the idea is that you want the pin to be square to the string at rest, roughly, which means that as you move the action a little bit by adjusting the height of the neck, the length of the string won't change appreciably. The guitar will stay in tune. Now, it's not exactly perfectly staying in tune, but for most of our purposes, it does. And it works extremely well. And it's the only way to get it, really. If you have an adjustment that tilts the neck, of course, that's going to change not only the pitch of the string, but also the intonation length. No system is perfect geometrically, but this is pretty darn close. This was inspired by my wonderful friend Jim Ham, a brilliant guy in Vancouver, Canada, who builds bowed instruments and bows and other stuff like that at a very, very high level. Makes his own CNC machines, that kind of guy. So back to this part of it. This is the neck we've been working on, and you can see that I didn't get this spruce pin exactly where I wanted it. It's a little bit closer to this side and this side than I wanted it, but there's still plenty of carbon and plenty of strength. It's not a problem mechanically. And after all, when the guitar is strung up, the force of the strings means that the pin only touches the top of the tube here and the bottom of the tube here. So those are really the only two places that touch. And as a result, it's okay for this to be a little bit loose. There has to be some wiggle in order for it to work. I put paraffin in here to help it slide smoothly. And it just works great. You can go from low electric action to any kind of slide action you want in the twist of a wrist, and it really works great. So I'll show you how this piece of hardware goes in, and then we'll put it together and watch it adjust and see how it works in real life. Okay, first a little history on this hardware. My first try was, gosh, almost 20 years ago now, was this part. This is an aluminum part with a stainless steel helicoil thread. Now, I'm going to have to make a metric disclaimer at the beginning here, because we can superimpose metric dimensions, but I'll be speaking in inches because that's how I grew up. This is how it is for me. And also, this important fastener, which is the heart of the system, is not, so far as I know, available in anything but imperial threads. So you can't even get a metric part. Maybe there's something else made in Germany or something that I'm not aware of. At any rate, back to the original part, aluminum, because I'm always looking for low mass if I can get it. So I used aluminum, and that meant that I had to install helicoil. And for those of you who don't know what a helicoil is, we'll provide a link here so that you can study it and see all about this useful kind of fastener helper. That means that because of the way this piece of hardware works, one side of the hardware is left-handed, and I decided that that should be the part that goes in the neck, because that's the way I like it to adjust. And it feels right to me, although you could do it either way. And then the other thing to know is that there's a matching part here, which is hidden inside of this tube. It also has a helicoil in it. So we're not threading the aluminum. We have nice stainless steel female threads for these left and right-handed threads to go into and address. Again, if you're not clear on this, what happens is when you turn the screw in one direction, it spreads the two threaded elements apart. And if you turn it in the opposite direction, it draws the two threaded elements together, thereby dependably adjusting the action of the guitar, okay? As I was saying, my first shot was this aluminum part, but because of this difficulty in getting the spruce just exactly where I wanted it, what happened was when I drilled the hole in the correct place, it meant that some of the hole was in the carbon and some of it was in spruce, which meant that this didn't necessarily go in the way I wanted it to do, and sometimes it would ooch over and lean into the spruce and therefore go off center. So I didn't use this for very long before I discarded that idea. Even pulled some out, as I remember. And then I used this part, which I made on the lathe, and this is a solid stainless part, so it doesn't need an additional piece of stainless on the inside. It's perfectly capable of taking the thread loads and wear over time. And so this is 304 stainless, a little bit tough to machine, good corrosion resistance, excellent strength numbers. The problem with this was it turned out to be devilishly hard to get a pretty knurl on my lathe, even though I tried very hard. And it's just not an easy material to displace. The toughness of the material makes it hard to knurl. And I finally got kind of fed up with that. And I shifted to a piece of spline shafting. That's what this is. So I can buy this from a supplier just like that. And this is this is a long piece of gearing, or spline shafting as it's called. And from that, I make these parts so I don't have to knurl them. They already have these teeth in them. And the whole point of this knurling to begin with was to keep the bushing from rotating in here, which would be a very bad thing. So these grab onto the spruce pin and lock it in place. So what happens is after this gets installed, I leak thin cyanoacrylate in there, and it turns the spruce into a kind of a medium hard plastic, and it locks it all in place. And finally, with the belt and braces approach, I drill a couple of tiny holes in there and pin the part with a little hard dowel pin made of steel. So kind of like a nail, a hard nail. All right, so that's the history of this bushing. And this is the installation tool, which we will be using in just a few minutes. All right, so I now need to hold this in the milling machine and determine the location of this part and then drill for the bushing. So I'm going to use this vise. And this is a machinist vise that's designed for special jobs. Precisely made. They're not very expensive, really. The global market for machine tools has brought the cost of all this stuff down. So just want to make sure that this is in the vise securely and bottomed out. on the bed of the vise so that the neck pin is square to the vise itself. And then this is just a piece of scrap material that's the same thickness as the vise, so that I can put it in the vise jaw, well, you'll see in just a second, and make sure the vise jaw stays parallel. So that'll go over here. That means I can I have to make a little adjustment. Be right back. All right, so just to be clear, these are the same size, so that it'll make sure that this vise jaw stays parallel to the back jaw when we clamp the vise into the vise. So we have two vices. All right, and then before we start to go to work, I'm going to put a support underneath the neck right here with this adjustable setup here and a smooth steel plate to protect the fingerboard surface. And I just want to make sure that there's support underneath so that when we go to press the neck bushing into the hole, we have some support underneath and it can't get moved and cause a problem. Okay? So now we can figure out how stiff this whole thing is. Pretty stiff. Particularly in this direction. All that carbon going in this way makes this incredibly stiff in that direction, and also incredibly stiff in twisting or torsion. Fabulous stuff. All right, this is called an edge finder. So with this slick little device, we're going to be able to locate these surfaces that we'll need to find in order to find the center. Okay? I'll show you how that goes. So we're going to move it towards the surface, and you'll see this part that's eccentric now will become more concentric as it nears the surface. When it touches the surface, it's going to jump sideways. If we look at it from this direction, we'll see it just as it jumps sideways. So I'm advancing it very slowly, and now it's moved. So it has so-called found that surface. Left side is 0, and find the other side. And then we'll ask this device to divide that axis by 2. Now when we move the X travel over to 0, it'll be exactly in the center of the part in this axis. Now we have to do it with a Y axis, same way. And there's our 0. And find the back side. So that's 0. So now, when we position the mill at 0 and 0, will be exactly over the center of the part. This last number is a distraction. I should really put a piece of tape over it. This last digit doesn't really mean anything. Just to be clear, and I think we'll do a riff about tolerance someday, but so decimal point, 10th of an inch, 100th of an inch, 1,000th of an inch, 1,000th of an inch is half the diameter of a normal human hair. And then over here is 1/10,000th of an inch, which who knows what that means, and certainly well beyond the accuracy of this particular machine. It's a fantasy to think that that 4th decimal point has anything to do with reality. It's a nicety that we've looked at it at all. My process notes here say plunge the big hole first, so that would be the clearance hole. We're going to put this in here first and plunge to 600 thousandths. So let's set a 0. All right, so and then this is the 1/2 inch hole. 0.500. So now we're going to set a 0 at the bottom of the hole we just made, and we're going to go 500 more for 1/2 inch depth. All very civilized. And because of the size of the bushing, we're not going to get involved in any of this carbon fiber, which would induce inaccuracy by throwing the part off. Okay, and then the last piece of our job here is to put the part in, and we'll just have a quick look. The end of this is turned down to help it start on center, which probably it doesn't need that help, but it's a nicety. So this is 500 diameter to match the hole we just drilled. Okay, so let's just press this down until it won't go any farther. Thankfully, we have there to help us. Now we're going to unscrew the tool. And then the last part of this will be to drop some crazy glue in there. But we're done in the mill, so we'll take it out now. Okay, so there it is. And here's our heroic fastener. And now we can demonstrate how this whole thing works. You can turn the screw and it adjusts the relative height relationship between this pin and the socket that goes in the guitar. Okay, so now let's look at the socket a little bit. There's a precisely cut hole in the guitar that's 1 inch square. We can buy this material almost anywhere. I mean, actually they have this at Home Depot and maybe your local hardware store. And this is an aluminum extrusion, which means the aluminum is molten and there's a die cavity that's exactly this size, so it's 1/16 inch wall thickness, or 0.0625 thousandths. It's 1 inch across in both directions, and so 7/8 inch square on the inside, so that's why this part is 7/8 inch square. So we're going to just check this to see, and you can see on the micrometer it's just not quite a 1/2 thousandth oversized. We're going to call that pretty darn perfect for commercial extrusion. And here it is, just a few tenths, or about 1/3 of a thousandth across flats on this other side. That's extraordinary, really, when you think about it. Again, we're talking about a fraction of a thousandth of an inch. A thousandth is half the diameter of a human hair. So measuring in a couple other places, here it is, a 1/2 thousandth over. Very nearly perfect. What happens is this aluminum tube, there we go. So now you can see how it adjusts. If we kind of push these together, we'll get both parts to engage and thread. And so you can see that this is a, almost zero effort to move this back and forth. And even when it's loaded with string tension, as I mentioned, it's only touching up here at the top and down here at the back. And so there's only 2 little contact lines. And when we lubricate those with paraffin wax, we get a really nice feel. And it just feels like magic. So easy to adjust. So that's the system. And we'll just take one last look here at this part. This is several little components, the tube we just looked at, and then this part, which I designed to squeeze in here. And so it's a light press fit. And then when it's pressed in, it makes the tube a little bit bigger because it expands it from the inside. So this is now a little more than 4 thousandths big here and 3.5 thousandths here. So just a little lapping on sandpaper. You can see the sandpaper marks on this one. And it brings it right back to the dimension we want, 1/2 thousandth under. In this case, that's fine, 1/2 thousandth under. So this is perfect, and it's ready to go into that hole. The only other thing that happens is you'll see that there's 2 little pins that are driven in here in holes that are carefully drilled after the 2 parts are pressed together, just to make sure that they can't move or become misaligned if somebody does something crazy. You never know what a customer is going to do when you hand them a wrench, I promise you. Who knows what happens in the solitude of their castle. So we just want to make sure that they can't do anything bad, like pull this assembly apart, which would be a very difficult thing to repair. So, and then my final little, well, I'll show you this in another video when we glue it in, but you'll see that the thread for this part, again, there's a stainless steel helicoil in here. The thread for this part does not continue all the way to the back of the part, and there's just a plain hole here. So what I do is, when this gets glued into the guitar, it's glued in with epoxy, and I just put a little wooden plug in there to keep the glue from getting inside this part and making a mess. After which it's easy to drill that out. You have to drill through the back of the guitar anyway, which I normally don't do until the back is all glued on and sanded and has a coat of finish on it. I really should talk about this fastener. This is the key to the whole system. It's made in Pennsylvania at this company, MACIT. They make all kinds of custom fasteners for industry. The parts are absolutely beautiful, first grade manufacturing. These are rolled threads, which are stronger than any other kind of threads. In other words, the threads are squeezed into place the same way that a knurl is made by displacing material. These threads are squeezed by a very special machine that grabs the part, rotates it in between several dies, and just mushes the steel into this perfect threaded shape. What that does is it ensures the best mechanical properties in the steel. There's no cutting in thread rolling, and so there's no tearing of the material. And in fact, the very nature of the process means that the material is compacted and crushed together, and it becomes even better than it was when it was just starting out as a piece of stock. So it's great. And then you can see that there's a hex end that's broached on each end of the part, so you can adjust it from either side. So you can choose to turn it either way when you put it together. In other words, you could make either part the right-handed part or the left-handed part. And I first saw this part in this tool 30-something years ago when I was working to found Parker Guitars. This is a cutting tool for the milling machine called a fly cutter. Scary looking thing, but it's not scary because it's balanced. And you can run this 6,000 RPM all day long, no problem. So this is a single point cutter. It would go in the milling machine and whiz around as fast as you want, up to 6,000 RPM. And this fastener that we're talking about is what holds this insert in place. It's called a clamp screw, and it's a terrific way to draw things together and hold them tight. Of course, on the guitar, we're not clamping, we're adjusting, but same principle. Unfortunately, these are not available metric. That you have to use the threads that they have available. Usually it's the same pitch on each end, although I just looked through their catalog before filming today, and I noticed that they do have a couple of differential threads where one side is 28 pitch and the other side is 32 pitch. Not quite sure what the meaning of that is. But at any rate, it's a fantastic fastener, comes in a variety of lengths and diameters, and as far as I know, is not available elsewhere. So get them while you can. The MACIT company, and we'll show a link here to their website. These surfaces that get bonded into the neck block, as some of you may know, it's quite challenging to glue metals with epoxies. They don't tend to stick very well. And the best thing you can do to help ensure a good bond is to sandblast this surface. So I take care to do that right before I glue it, before the oxides can form, like the minute before I put glue on it. I sandblast it and push it in there and bond it. And I've done testing, and boy, it's really stuck. It's not going anywhere. And it helps to strengthen this whole area. You can see there isn't a whole lot of material in the neck block anyway, and this makes it a little bit more rigid, or maybe a lot more rigid. Anyhow, that's my crazy neck joint.